Welcome everyone. Welcome to Clary. We are very pleased to be hosting again Silicon Valley Deep Learning Group. SVDLG is very kind in our hearts. We are again, welcoming you with a lot of the, basically we want to host as many meetups as we can and really spread the word about deep learning in the community. Just a little bit about what Clary actually does. Clary is enterprise software. We are transforming the way businesses do their work, starting with sales. Our emphasis is on really analyzing a lot of the data around sales activity and applying machine learning, deep learning, and predictive analytics on all the data that relates to everyday sales activity. We also take a lot of effort in forecasting the very best forecast for businesses so they can meet their numbers that they predict to Wall Street and financial community. So from the perspective of what matters to companies, we are really about making it streamlined for sales teams. As you all know, sales is the lifeblood of a company. If you sell more, the company grows, shareholders are happy, the community is happy, customers are happy. So sales is very near and dear to our hearts. And for us to be able to make an impact by way of improving how people sell, by giving them machine learning and data science-driven insights, that fundamentally makes it a better world for everybody. So, that's our mission. And we have a number of engineering positions open, and we encourage you to check us out and see if Clary is the right company for you.
Let me introduce Forrest landola, and I have some great bio information for Forrest here, but I haven't memorized it all. So let me tell you that that Forrest is the CEO of DeepScale company, and they do perception for autonomous driving. Forrest himself graduated from UC Berkeley with a PhD in electrical engineering and computer science in 2016. At Berkeley, Forrest was involved with the Berkeley Deep Drive group and a number of other research centers on applying machine learning and computer vision to practical applications. His advances in research on scalable training and efficient implementations of deep neural networks led to the founding of DeepScale, which you can find more information about at deepscale.ai. DeepScale has a core technology in training machine learning algorithms, rapid deep neural network training, ground-up redesigns of deep neural network architectures, and efficient deep neural network deployment in embedded and IoT applications. DeepScale has focused the skill set on automotive industry. They currently have a number of customer engagements. So please welcome Forrest landola. He's going to give us a great talk.
Can you hear me? Great. I think we might have some feedback issues on this. No? Okay. So, thanks to the Silicon Valley Deep Learning Group for organizing this, and to Clary for hosting this. I'm really glad to be here. They made it really painless for me to come and do this talk. They were very well organized. So I'm going to be talking about not only perception systems for autonomous driving, but also more broadly, what are the key ingredients that you need to build perception systems and use deep learning effectively. So I'm curious, how many people in the room have used some sort of deep learning before or got their hands dirty? So pretty much everybody, it looks like. And how many people are kind of, whether in a professional capacity or tinkering, playing with autonomous vehicles of some sort? So a few, maybe 1 in 10 people or something are trying to do that. So I think this talk will be well tuned to this audience because I'll give you a few nuggets on kind of our approach and how we apply to the autonomous driving space, but it'll also give some general wisdom that's been hard earned by us on how to do deep learning for practical applications in an effective way. I've gotten to give this talk a few times now, but this is one of the only times I've had a chance to spend a whole 30 or 40 minutes to kind of give you the full rundown. A few times it's been kind of limited to 10 or 15 minutes or something. So I'm going to kind of dive into some of the nitty-gritty details and some technical results as well. But the main roadmap for this talk is, I'll first just kind of emphasize what you probably already know, but kind of dimensionalize a little bit, that deep neural networks are changing many areas, and maybe even every area. We focused our DNN sort of skills on the autonomous driving market and solving some fairly particular problems there. And then I'll spend a good chunk of the talk on sort of giving my best shot at explaining what are the key ingredients for success in applying deep neural nets to your application. So our team's growing quickly, but these are the 5 core technical people on our team who have been with us for a while, and we've got a bunch of offer letters out right now and stuff. But so myself, Forrest, Matt, and Anting, we all went to graduate school together at Berkeley. And these are 2 of my favorite people from Berkeley, and we hired a 3rd of my favorite people from Berkeley on the right, Kurt Koitzer, who was actually my PhD advisor. So I even brought him into DeepScale while I was still a graduate student. And it's funny, they have some rules at Berkeley about professors not being able to hire their students as, if they start a consulting company to kind of avoid slave labor. But there aren't any rules about students hiring their professors, so I just went ahead and did that. And so eventually I even bumped him up to being a co-founder, and he's actually starting to ramp down his career at Berkeley and ramp up on DeepScale full time. And then finally, Don McMillan, who we hired just recently. This is his 5th time being a VP of engineering, and he's extremely good at it. He also happens to have a background in optics, which is super useful for computer vision and what we're doing. So if you were to ask me, this is a machine learning or deep learning meetup after all, if you were to ask me just a few years ago, I want to learn about machine learning, what algorithmic tricks or techniques should I be aware of or start to learn about? And the answer varies widely depending what problem you're trying to solve, at least at this time. So this was text, this is audio, this is vision. So there are certain sort of algorithms that were good for text, and they're kind of often one-off or a particular recipe there. Likewise for different audio problems, and likewise for computer vision problems. And a lot of the time here went into, when you built these things, to finding the right algorithm sort of from the ground up. But in all of these particular problems, the exact same benchmarks and everything, today the best solutions out there are based on deep neural networks. And some of these things like that 16-layer DCNN over there, there's actually some even better ones now, but they're all neural net based to get the absolute best possible accuracy on these problems. And so in some ways that's a nice sort of focusing element, that we kind of stay in this end-to-end training family of algorithms. On the other hand, it's not like there's one deep neural network that magically solves all these problems in the best possible way. It's more like there's a different deep neural network recipe that's been discovered that does well in all these things, and there's no reason to believe those recipes are the best they'll ever be. People are still pushing them forward. So the way I kind of summarize this is finding the right DNN architecture is replacing broader algorithmic exploration in many areas. So another way to look at this is, Alexei Efros, or his nickname is Alyosha Efros at Berkeley. He's one of the big shots doing computer vision. And he says, my students used to design algorithms and write software, but now they mainly design neural nets. They're neural net architects. So that's kind of how much things have changed. And Andreessen, by the time Andreessen said that software will eat the world, I would actually say that by 2011, software actually had already eaten a lot of what there was for software to eat. And without machine learning, what software can really eat is stuff where you can kind of write down a procedure by hand of modular loops and so on. It's a particular if-else logic. But what that can't solve without machine learning is when there's no equation that kind of you can just write down that solves the problem that we're aware of. And it turns out, the part of why I put text analytics, speech, or audio, and vision in the previous slide is because those are 3 areas where, for many of the problems, there's no equation that we can dream up that really adequately solves the problem. So that's kind of why, those are areas where neural nets will continue to keep taking bites out of things. And so, we kind of set out 2 or 3 years ago to figure out what would be the area, given our expertise in deep neural networks and accelerating computation of deep neural networks and so forth, what would be the optimal area for us to go in and build a business and create value? And we thought about lots of things. We looked at computational finance, we looked at algorithmic ways for doing insurance adjustment and looking at and deep neural nets for figuring out the value of a house, and all these wacky things. Went and talked to lots of customers, hundreds of customers. And meanwhile, through that exercise, the auto industry started reaching out to us. So, basically we started getting this inbound interest of people who said, look, my company will go out of business if we don't build an autonomous car. And we don't really understand how to solve the perception problems. And that was a big eye-opener for us. Maybe 8 or 10 months ago, that kind of started to happen. And we dug in deeper, and basically what we figured out was that the autonomous driving market, or just the car market, is a $3.5 trillion industry. And that industry is being disrupted right now. It's having the biggest disruption it's had probably since the assembly line in the 19 teens and 20s. And so we see this huge opportunity to help catalyze that disruption and take things to the next level. So in terms of autonomous driving, we probably should spend a minute to level set on what exactly I mean as far as what are the building blocks and how do we go about doing it. So this is sort of my cartoon in 5 boxes how to implement autonomous driving. So you want the best sensors that you can afford given the price point at hand. You want to be able to eat those sensors in real time and produce some sort of output that a path planning system can understand. You ideally want some form of offline maps that contain everything that you can reasonably pre-compute about the environment. And you may want to fuse the real-time perception output and the offline map output to create an environmental model, or these may be separate inputs to a path planning system. And then the path planning system outputs a particular sort of motion plan, and the control system figures out how to actuate that and send the car on its way in that direction. So all levels of vehicle autonomy, so the NHTSA levels are levels 1 through 4. The SAE are 1 through 5. So I'm doing the NHTSA 1 through 4 levels. So level 2 is basically, it kind of boils down to driver assistance. The driver is still fundamentally in charge, but the driver is being assisted by a car that knows how to keep itself in the lane, keep a safe following distance, and so forth. All the way up to level 4, which under the NHTSA standards may not require a steering wheel. So all of these autonomy levels need this type of flow to work, and of course the more control you want to give to the car, the better this flow has to work. And talking to a number of people who are attacking this problem right now, they're finding that perception, this green box here, is the most challenging aspect of this whole enterprise. And this will kind of ring true with what, I saw a talk earlier this week by Sebastian Thrun. He gave, just up the road here. And what he said was that the autonomous driving problem, software-wise, is something like 90% perception and 10% control. And that just makes so much sense to me because, I'm not saying path planning and control are easy, but we've been doing it for a long time as a community. So the first completely autonomous takeoff transatlantic flight from the US to Europe and landing happened in 1947 by the US military. And we've all probably this year flown in fully autonomous planes. And the reason that's worked so well, it's not because the control problem is easier. It's a 3D problem, whereas the automotive problem is a little bit more 2D. The reason is that we've had autonomous planes for so long is because when we're in the air, there just isn't that much to hit. And what is there to hit is a lot of it is mapped on regimented displays that air traffic controllers, et cetera, are making sure are working perfectly. And so that kind of points to the perception being one of the biggest challenges. And another piece of this is the offline maps work, are really useful, but they can be, surprisingly expensive to build. So my hunch, I don't know if a lot of public information is available about this, my hunch is the reason you mostly see the Google Panda cars only in Mountain View is because they've mapped that like crazy. And they have annotators who have gone down probably to centimeter level accuracy perfecting that. And they probably try to even get construction zones and so forth onto the map. And that's just not scalable for a nation or a world. And so I think there's no other obvious path to me besides us being a little less reliant on the offline maps and more reliant on the car in real time to understand its environment. I'm not saying you want to get rid of maps, but that shift is going to happen to get to everybody having an autonomous car in many areas. And so finally, I mean, there's a certain threshold to this perception you have to get over to get to the next level of autonomy, and that's going to be true for a while here. But I think there are 30,000 accidents a year in the U.S. It turns out, I think it's IHS or NHTSA says that actually 94% of those are caused by human error. But in any case, until we're down to like 0 accidents, I think improving the perception system will always be a really important factor in improving safety. So I think we're going to have a job for quite a while here. So you may be wondering by now, what the heck does DeepScale actually make? So we take LiDAR cameras, and currently this is it, but potentially other sensors as they start to emerge, or if radar looks particularly interesting. We have this perception module that contains currently a commodity processor, and long term we may go a little bit beyond the commodity processor. And it outputs an environmental model. So I should have drawn this, but we'll get there eventually. Object lists, occupancy grids, that's on the road, what areas of this road is actually drivable. Motion understanding, figuring out where the lanes are, and so forth. So these are all areas that, in one way or another, a company called Mobileye has sort of attacked. But part of why we got all that inbound interest from automakers is because they told us in sentence 2 or 3 of the conversation that Mobileye isn't meeting their need, either currently or in their sort of roadmap, of getting to the right accuracy levels for these things to be able to climb the autonomous driving chain in terms of level 3 and level 4. Mobileye also says they talk about they're going to do deep learning, or deep neural net inference on their chips. My understanding, reading the roadmap that they give out, it's not going to be till 2019 when the IQ5 chip, we're currently in the IQ3 chip, comes out. So that's quite a ways for us to do some damage here. You also might be wondering, so how would I draw sort of the landscape of autonomous driving or perception systems and sort of the ecosystem? So, I can't fit everything on here, but this is actually, I would say, fairly comprehensive. So this is us. We're sort of drawing this as, this is what we do, and then what are the adjacencies. So this is the old guard of people who have been trying to provide stuff like this to the auto industry. Other folks who have the same kind of raw talent as we do. At one point, we thought the internal teams, automakers and OEMs might be, they might really want to do it themselves. They might kind of be saboteurs to our business. But the reality is, cars are really complicated, and automakers basically, whenever they can find a good solution to a problem, they'll use it. And they've told us such. So these are our close partners, and we're working with BMW, for example, on a proof of concept. They're full system autonomy companies. Some of these may remain full system autonomy companies. I suspect that some of them will, as their ship dates become closer and they have to actually put a product out there, will start being more friendly to the idea of bringing in solutions rather than building it all in-house. And then Drive.ai and ADAS Works are 2 of the only startups we know that are trying to kind of tackle some adjacent turf to what we're doing. I think there'll be room for all of us, but they're kind of in the same area, came from a similar background as we did, and so forth. So that, in the high level, is the autonomous driving aspect of this. But I know only maybe 1 in 10 of you here are doing autonomous driving in your career or outside your career. So I'm going to talk about key ingredients for success with neural networks now. And DeepScale's mission is to build the best perceptual systems for autonomous vehicles. And there are a number of core capabilities in deep learning that we must have to achieve this mission. And given this is a deep learning meetup, I'll focus on these core capabilities and present some of what we learned about this that's applied to us but may also apply to you. So if you want to actually, not just build, experiment, but if you actually want to build a product that has deep learning somewhere in the middle of it, I think you need these 4 capabilities. So you need to be able to train fast, because searching for the right neural net models is currently an empirical science, and the theory is way behind the practice right now. You need to be able to train fast also because data sets are getting bigger really quickly. So my understanding, and I haven't gotten Tesla to exactly confirm this, but my understanding is that Tesla, when the user is driving down the road in autopilot mode, and the user says, no, bad Tesla, I'm going to turn the wheel a little bit. What happens is the Tesla actually logs a few seconds worth of training or worth of data from at least the cameras and maybe other sensors. And when the car gets back to, say, a Wi-Fi connection in your garage, it'll share that data with Tesla's, it'll upload to Tesla's cloud, and Tesla's QA team will go in and say, okay, so what was going wrong here? Clearly, the user took over. That shouldn't have had to happen, so what was the problem? It could turn out that something as simple as there were lanes missing on the road, or lane markings missing, or the lane markings and lane splits were weird. Okay, that happens. So the Tesla QA team then would go in and label what's going on in that image and add that to the training set. And if they're smart, they'd go find a bunch of similar images with the same problem, or more of the weird lane markings, add those to the training set, and then they deploy a new model to the car that no longer makes that mistake. And so you can imagine with lots of cars in the wild all having user takeovers and various issues like that, you get lots and lots of signal out of that, but that means your training set grows really quickly. And if you can't train fast, you can't ship those new models quickly. Along the same lines, when you try a new neural net architecture, you have to re-ingest all that data and often make multiple passes through it. So fast training is really important. And then finally, once you've found something that's very good, you want to put it in embedded hardware at reasonable cost, both in terms of power as well as the cost of the hardware. And you want to have the ability to keep pushing new models to that as you find better ones. So I'm going to go deep on at least 3 out of these 4 things. I won't do a deep dive on annotating training data, although I can maybe answer some questions on that at the end. But let's spend a couple minutes on training rapidly. And before this session, I got a couple good questions about this, so I'll try to give one more level of detail on that. So we're good? Okay. So, I guess the logical question to start with is, what are the options for accelerating DNN training? And by accelerate, I mean compared to what most people would do on a workstation sitting under their desk, what can we do better? So one possibility is, at least in the computer vision and visual processing stuff that we do, this computation called convolution is where most of the time goes. This figure's a little small, but basically this is showing that 90% of the Google net neural net architecture, the execution time spent on convolution is 10% is everything else. And we've actually managed to squish everything else down a fair bit with faster kernels, whereas the convolution, sorry, this is really small on your screen here. The convolution is pretty well saturated. So we're already at a point where, even though 90% of that time is convolution, existing libraries, at least on NVIDIA GPUs, can do 50 to 90% of what the peak theoretical upper bound of what that processor can do. So there isn't a lot of juice left to squeeze there. So one option would be, I could put more GPUs in my workstation, right? And it turns out that folks at Facebook and Flickr and elsewhere have been pretty successful at this. It's pretty well understood how to have an 8 GPU workstation and saturate that pretty well with a variety of deep neural net training applications. But how about scaling over a cluster of GPU-enabled servers? So in our Fire Cafe framework, we enable that. And there's a paper down here you can read on that we published at CVPR this year. But I'll go in a little detail about, okay, so the next frontier really is distributing over a large cluster of servers. Let me show you kind of how we do that. But first, here's sort of a warm-up on how to train on a single server or a single GPU. I think this is kind of important background knowledge. So going from left to right, like if this is a cat image, you'd hope that the output would be cat, right? But if it says dog or something else, you go from left to right doing what they call backprop. And there are 2 kinds of backprop signal here. There's a gradient with respect to the data and the gradients with respect to the weights. And so these weight gradients are summed, the data gradients are separate for each image in a batch. So usually there's a batch of, in this case, 1,024, but you can kind of pick how many to do between, how many images to do between your update. And then this one, they're separate for each image, but down here, it's you actually sum them up across images and produce one summed gradient update. That's even true on a single server. So now we're going to talk about strategies for scaling beyond a single server. So I've got roughly kind of 4 approaches I see that make sense, or that are worth considering at least. One is what they call pipeline parallelism. So like, it's a little hard to read on this projector, but these are each neural network layers, and each one gets a different worker, right? So perhaps a different server. And so one of the problems is parallelism is limited by number of layers, and the communication has to be dominated by which layer has the largest output, and you kind of block on that. So it's hard to kind of, you really kind of get eaten by Amdahl's law easily with this setup. And at least for training, I don't recommend it. For inference, if you have a chip and you can do spatial parallelism on that chip, that would actually be kind of cool. But for training, it doesn't make a whole lot of sense to me. Another approach, and I saw some people at Microsoft Research do this a couple years ago, is to have a different model for each quadrant of the image, so you can just divide it up sort of embarrassingly parallel. Sounds good, but like nobody has gotten like a good benefit from it. So it's a great way to keep 4 times more servers busy during training. It's not a particularly good way to get a higher accuracy level or less time to convergence. So this didn't make a whole lot of sense to me. And this approach is called model parallelism. So it's like in each of the layers, so each of these, each of these is a layer. So give a subset of the weights to each worker. And so for some classes of DNNs, this is a scalable approach. And we'll talk about when this does or doesn't make sense in a bit. And then finally, there's data parallelism, which is let's give a subset of each batch of the neural net training to give images 1 through 8 to GPU 1 and the next 8 to GPU 2, et cetera. So sort of important question here when thinking about given your application, which of these to focus on is, so what does your neural net actually look like? So this is how I draw a convolutional layer. And so like this green thing is the weights. So it's like a filter where this is how many channels you have, and then this is like, it could be a 3x3 filter. And then the black one is the input data to the layer. And I only have like a 2-dimensional screen, and I've sort of faked 3 dimensions, but there's actually 4 dimensions to this. So with the weights, there's actually multiple filters. So however many filters you have here is how many channels your next layer gets as input. And then the input data to this layer, this is only one sample. Usually there's a batch size, so 512 or 1024. And so as a result of that dimension you can't see, it can actually go either way. Well, these are 2 types of parallelism we already talked about, but it can actually go either way in terms of whether W or D is bigger. So model parallelism is more scalable if, and by scalable I really mean requires the least amount of communication, because that's what we're trying to avoid, if there's more weights than there is data in each batch. And then data parallelism is more scalable if there's more data than weights per batch. So to give you an idea of what you see in practice, so for a neural net called GoogleNet version 1, if you choose data parallelism to the model parallelism, there's actually 360x less communication required. So data parallelism wins by a landslide. And that's really common in whether it's computer vision for video or images or LiDAR, et cetera, because this height and width is usually way bigger of the data than the weights. So you often end up in that situation. So as a result, given our orientation towards automotive and so forth, vision is something we care about a lot more right now than text or audio for what we're doing. So we focused almost entirely on data parallelism in a flavor called synchronous data parallelism. So the conventional wisdom might be that what we really ought to do is just try to get all the dimensions of parallelism in the problem. So we use data parallel and model parallel and pipeline parallel all at once. And so Google and CMU and others, especially in their early work, did a lot of this stuff. And it turns out you really want to just find the simplest kind of parallelism that scales well, and then refactor all other aspects of the problem in service of that type of parallelism. And given a finite number of brain cycles in a day and lines of code you can write, this is an approach that's much more efficient for getting developers to produce efficient results. So there are a bunch of ways of harvesting data parallelism. So you can architect the most efficient distributed communication you can by figuring out, okay, so what's the upper bound of bytes per second I can transfer, and how close am I to that? And then can I do as few, can I do as few bytes as possible total? And then, architecting the computation as well to be as efficient as possible. So these are some of the ways to harvest more data parallelism. Now, as far as how to implement this, I'll talk about synchronous versus asynchronous for a minute. Is everybody kind of interested in this, or kind of bored? Okay, cool. I can never tell with these when it's kind of something deeply technical, whether it's like, wow, this is so cool, or like, get me out of here. So, okay, so I guess some people care about this. Well, I'll keep going. So, with asynchronous training, basically the idea is you have some central parameter server typically, and then you have individual workers that each have a copy of the model. But each copy from each worker to worker will differ slightly. And the reason for that is because in asynchronous training, each worker gets to choose to communicate whenever it feels like it. So there are some pros and cons to this. So one pro, I guess, is that asynchronous does give you kind of built-in fault tolerance, because if one worker goes down, well, you just kind of ignore that and keep moving along, because everybody has their own model, which is kind of valid. But there, on the other hand, there's this issue of gradient staleness. So like, if you end up being very bogged down by the communication, you can end up in a point where each update, the update from this only reaches here several batches later, at which point the gradients are kind of stale. And another problem is that the parameter server invokes a big communication and computational bottleneck, and I'll talk about that more in a bit. But you can imagine sending everything to this one server, even if it's a bank of servers, tends to get very bottlenecked compared to if you could have a more hierarchical approach. Does that make sense? I mean, so if this server, if let's say this is one piece of a bank of parameter servers, this only has one network card. And just hearing from this one server will saturate its network card completely. So you can end up where you have this, say you have 128 of these workers, where they're all waiting on sending to one server, and it really becomes sort of a mess. Synchronous data parallelism you could also implement with a parameter server and just make sure everybody communicates at the same time. But it actually gives you, using Synchronous gives you this great opportunity of having all the different servers work together in a hierarchical fashion that I'm not entirely illustrating here, but they all work together to sum these gradients and then get the sum back on all the servers. And has a few trade-offs. So it obviates the gradient staleness problem. So this literally gives you, if you implement it right, the same numerical results as a single server, a single GPU would have given you. Just using more servers. So it should be completely regression testable and so forth. It eliminates the parameter server overhead and allows for lightweight communication like reduction trees, butterflies, or rings. But you do have to do your own fault tolerance somehow. So a common way to do it is just by checkpointing every so often. If one server goes down, you just reset the whole group of servers to that checkpoint. So what do you want? Which works better? So this is synchronous parameter server versus synchronous reduction tree, this is basically higher is better. So this is number of weight gradient updates per second. So you want to do as many updates as you can per second. If you just this is just the communication part only. But as you can see, by 16 servers, you're really running pretty. You're doing like one update per second or something, and on the other hand, this green line is if you use a reduction tree, which is one of those collective communication operations that you can really only leverage, from what I can tell, if you're using synchronous training. So you can see here you're doing something on the order of 20 updates per second and 128 nodes with reduction tree, but with the parameter server you're doing less than one. So the reduction tree scales way better than the parameter server approach. And so I'm going to do some practical examples now with actually speeding up some real neural net training experiments. But yeah, of course.
When you say data parallelism in the context of using the video input, are you sending each of the video frames to one of these processors in a round-robin fashion, or just make it more concrete what you mean by that?
Oh, yeah, that's a tuning parameter of this. So you could decide to, that's an implementation decision of yours. So you could decide to say, I'm going to give multiple video frames of the same video to different servers, or I'm going to kind of break them up round robin. Within a batch, at least, of frames, it shouldn't make any difference who gets what, because it's computing the same thing. Across batches, there's some trade-offs. So if I were going to do multiple frames with, and actually try to get them temporally adjacent, I might actually add in a layer that deliberately understands that, like a long short-term memory LSTM layer that tries to actually follow the data through those layers to do, could be for tracking or just to do better recognition. But like these principles just apply given any, it doesn't care what's in the data, right? It only cares about how much computation and how much communication. And so it's up to you to choose what to stick in there in terms of the actual data.
I guess I'm trying to clarify, when you have data parallelism, do you have different neural network architectures running on each of the systems, or the same architecture?
Same architecture. Yeah, so if you end up with synchronous data parallelism, if you end up after some time step in the training where two servers have different neural net, not say it's still the same architecture, but if they have different weight values, that's a bug.
That's the bug.
Yeah. Yes.
So all these, as you said, all these techniques apply, but how about also be smart about our training process, which is take the hyperparameter space and try and see what's the fastest way to get.
I see. Great question. So your question is, can we find better hyperparameters and configurations that train faster? Absolutely. I'm going to get to that in a little bit, in fact.
Okay.
So just briefly, choosing deep neural net architectures to accelerate. So this is about 87% accuracy on ImageNet, top 5. And ImageNet is a data set I'm using not because of autonomous driving, but because a lot of people compare on it, and it's sufficiently large, more than 1 million images to kind of be interesting in terms of training times. And then this network and Alexson are both around the 80 or 81% accuracy mark on this data set. So the interesting thing about this is that you might think that throwing more parameters in the model would lead to higher accuracy, but the reality is that, now remember SqueezeNet from the previous slide, so what that buys you is 50x smaller model without any compression and the same accuracy level. And if you apply deep compression to SqueezeNet, we teamed up with the deep compression team over at Stanford and did this, we got this down to a 510x smaller model with the same accuracy level. So these over-the-air updates are now smaller than most of the apps that update on my phone that I don't even notice they're downloading. And so combining CNN architectural innovation with model compression, we got a 510x smaller model. But you might ask more broadly, so how did we get here? And what other neural architectures were we exploring when we found this? So we'll talk about that. So how did we explore this space? And what's our general approach? And then what are some lessons that we learned? So okay, let's do that for a minute. So FireNet is a broader family of architectures of which SqueezeNet is one member. So sort of the observations are fewer weights in the model leads to more scalability, and 3x3 filters have more weights than 1x1 filters, and it's really 3x3 by channels, 1x1 by channels. So can we exploit those things to get neural nets to do good accuracy on a smaller budget of parameters or faster training? So in detail, this is what a Fire module looks like. I've sort of drawn this as Legos, where this is like the channel dimension, and this is multiple filters in each layer. Let me skip this. So a couple interesting trade-offs to go straight into the question of when you start tuning these hyperparameters, what happens. And this admittedly is all with the same training protocol, which we've also optimized sort of independently of this. But this goes straight at the question of how, given some neural net architecture that we design, how do you choose how many filters to put in it and where to put those filters and how big they should be? So the squeeze modules get their name because they have fewer filters than the expand modules in this setup. And then our question here is just what trade-offs occur when we vary how few filters to put here, kind of squeezing it down. And so what we learn is, so this one here is SqueezeNet. It gives about 80% accuracy with 4.8 megabytes in weight. So you compress it to 1/10 that size with compression. But over here, things kind of level off. So the difference between having a squeeze ratio of 0.5, where you have half the number of filters here than here, versus 1, you change the number of weights by about a factor of 2 in the model, and also the computation by about a factor of 2. But you only change the accuracy by like a couple tenths of a percent. So there are these kind of saturation points you can look for. You want to kind of find those points where throwing more parameters at the problem in that dimension doesn't help you, and then stop there. Or start with a fairly parameter-heavy network and keep backing off until you start losing accuracy. Is kind of how we think about it. Another kind of similar study we did was, so within these expand layers, how do we bucketize like how many 3x3s versus how many 1x1s given a particular budget of filters, number of filters per layer? And there's a similar threshold we find. So like whether you put half the filters here being 1x1 or you put them all 3x3, you get the same accuracy. So there are points in the design space, and the big lesson here, where throwing more parameters at the problem doesn't help accuracy, and it just wastes communication and computation. So I think, in lieu of a comprehensive theory that tells you everything there is to know about deep neural net design space, I think you want to at least be cognizant of sort of this set of saturation points and looking for them. And then, I've been preaching the whole talk that like if you just have fewer weights in your neural net, you can train faster. So let me kind of demonstrate this. So this is GoogleNet, and as mentioned earlier, 47x speed up on 128 GPUs, and a relatively modest like 60x speed up on 256. And the problem really is just the communication time of this 53 megabyte model is sort of killer at that point. So what we did was come up with a 13 megabyte model with about the same accuracy that has a little less computation than GoogleNet, per iteration, but actually trains much faster at 256 GPUs. So we have 145x faster compared to a 1 GPU baseline on 256 GPUs here. And I haven't seen anybody else scale to 256 processors really at all. So finally, has someone taken a picture of that? I can.
Are you posting the slide?
I could do that, yeah. Okay. Yeah. So the last thing, and I won't go deep on this, but just briefly. So once you find an acceptable model, you want to deploy it on embedded hardware for most applications that aren't in the server. So autonomous cars would be extremely inconvenient to try to run the whole perception stack on the server and communicate in real time, and it'd be pretty unsafe too. So we want to run it in the car. And so most folks who are doing deep neural network right now, I would say, are, well, really especially for vision, are kind of a slave to what libraries they have available to them to do efficient computation. And so, NVIDIA has done a great job of providing libraries that run efficiently on their hardware. And, other vendors haven't done as much of that, although Intel has really stepped up to the plate lately and done some of that. But we have this system called Bodhi, which is actually open source, github.com/Moskowitz/Bodhi, which does portable and efficient deep neural network inference. So on the NVIDIA hardware, it's similarly efficient to NVIDIA's own libraries, although the good thing about using Bodhi is if you don't like how something works or it's too slow or not tuned for that problem size, you can always go in and fix it because it's open code. And then we also run this on Qualcomm, and so we're running at 50 to 80% of the peak upper bound flops per second of what you can get in the Qualcomm embedded GPU. And then we're working on other architectures. We've been building partnerships with Intel and so forth. And there are lots of different DSPs and things that are exciting to run this on. Basically, what we really did here was to generate OpenCL code. So OpenCL is a CUDA-like language that runs across multiple processors. And rather than just writing one particular set of computational kernels, we have a sort of pseudo compilation flow, you could call it, that generates a variety of different configurations and is able to do some auto tuning and allows you to kind of plug in new code gen flows as well. So if you compare that to writing new kernels for each processor, this is a much better use of developer time. So I think I'm pretty much at the end. I'm at about 40 minutes, and yeah, let's wrap up and take some questions. But before I do, just to recap. So deep neural nets are changing lots of areas, especially ones for which there's no good closed form solution. At DeepScale, we've really focused in on perception systems for autonomous driving. And we'd love to talk to you about that, especially if that's what you do for a living. But on the other hand, I think some of the key ingredients that we need are actually pretty broadly necessary for success with deep learning. So fast training, the right training data, the right architectures, and efficient inference. So thanks very much.
All right, thank you for that great talk. So as following our usual tradition, we have some period for question and answers. And I have a mic, and Chris over there has a mic. You can bring it around. And please remember when you do ask a question to stand up, have a microphone, and introduce yourself. Give us your name and tell us where you're from. Also, apparently there's a vehicle, maybe a motorcycle, that's outside with a headlight on. And so if you own a motorcycle that's capable of that, it might be yours.
We can help you roll start otherwise. It'll probably,
Okay, first question. Chris has got the mic.
Does it work? Or not? Does it work now? Yeah. Hey, I'm Tommy Marla. It was from a company called JKI. It was a great presentation, really interesting. One thing you didn't really attend was when you actually move those nets to sort of the embedded platform, how do you guarantee real-timeness of the perception? I mean, you have like 10 milliseconds to make a decision where to steer the car.
Super good questions. So how do we guarantee real-timeness? So in some visual recognition algorithms, like decision trees, for example, you can actually end up in situations where some decision tree evaluation flows are longer than others, or there are other kinds of cascades and stuff. So in those cases, what you're talking about is a really big concern where there can be a big gap between what's the fastest and the slowest, worst case execution time. In the case of most neural nets, and I guess probably most people have kind of seen this in their experience, you can tell offline exactly how many multiply adds you're going to do because you made the neural net architecture, and it's like once you've finished deciding what the weights are, everything is pretty much deterministic. There is no branching really in most of the stuff that we do. So I think branching is the enemy of worst case execution time clarity. But fortunately, we don't really do much branching in our stuff, so that's not been a really hard problem. Does that make sense?
Yeah, and are you using like real-time OS that then actually executes the inference?
Yeah, as far as the real-time OS and so forth, I think that becomes a bigger problem, right, when you have lots of different things running on the same chip. And we just haven't hit that situation yet, but I think that real-time OS or some sort of partition time slice OS would be a good choice once, if you end up running lots of things in a single chip rather than kind of having a chip per core functionality.
Next question. Please be sure to always talk into the mic, because otherwise it doesn't make it onto the video on YouTube.
Hi, thanks a lot for the talk. I'm Lei. Actually, I'm the data science lead at Clary. So it was a great honor to host your talk. So I have one question: is like, how is your work compared with TensorFlow, like in terms of speed and also compatibility, like trying to deploy into different devices?
It's a great question. So I think I could sort of divide this. Let me see if I actually have the right slide in my deck here that sort of help to illustrate. Let me see. There we go. I found the right slide. Okay. Well, this boots up and shows you a nice view of Yosemite. So I sort of slice this all up into there's the neural net architectures and training configurations, and there's the computation implementations. But I guess if I got to redraw this picture, I'd slice this into two buckets. So there's the productivity layer of what are the wrappers around the computational kernels, and then there's the computational kernels themselves. So I feel in Bodhi and also in cuDNN, kind of the core contribution is efficient kernels, and you can wrap those in whatever you want. It could be TensorFlow or Caffe or whatever, and those are sort of useful convenience layers on top of the kernels. And likewise, with the communication implementations, you could use messaging.
Hello. Hi, my name is Tzvi Ackler from Optimizing Mind. We focus on explainable AI. I was wondering, so the way you compress or make more efficient the number of parameters and so on, I'm wondering how sensitive that is to the specific problems and the specific tests. Because you showed benchmarks, but what if you change what you're trying to do? You have to change.
Yeah, good question. I mean, I think I haven't found that many kind of clear-cut, you can make this change to any neural net and it'll be equally happy kind of things. But I have found, or I guess we have found, especially my colleague Song Han, who helped out or did a lot of the stuff in this work with the compression side, we've sort of figured out a set of sort of useful experiments you can do given a neural net architecture to kind of figure out which layers are most amenable to compression. So the trick that we played was we took a net and we went through each layer one at a time. And we didn't, at this stage, we didn't retrain because there are lots of layers and that might take a little while. We could do that. But what we did was for each layer, we'd delete half the parameters and then just leave the model alone and run it forward on the test set and see what it does. And it turns out there are some layers where deleting half the parameters is catastrophic, and others where it's didn't really care. And so you can do, I think we call it sensitivity analysis. And then once you kind of find through that heuristic search which layers can really be just kind of beat down, you do that, you beat those ones down, and then you could do a little more training with your new sort of blinded in a few places model and make it perfect again. Does that help?
I'm Ramona, and I'm working at Future Mobility. My question is related to autonomous driving. Usually the approach of doing deep learning for autonomous driving is either an end-to-end or a modularized architecture. So an end-to-end is basically you have a deep network between your perception and controls. Which one you favorize, and what you are implementing in your approach?
This is a great question. I think both of them are useful. And this might take me a minute or two to explain, but I think it'll be worth it. So what Ramon is saying is that you could break each of these, at least perception, planning, and control, into like a separate module or even set of modules that you kind of, there may be learning there, but it's like kind of local to that module. Or you could take sensor input and try to generate the control output. Out of the automakers that we've talked to, not under NDA, Volkswagen seems to be the one that's kind of most active at trying the end-to-end thing. Other automakers seem like a little more conservative about that idea. So in some sense, we have to kind of try to meet with our customers. They have a big picture of how the car will fit together, and we have to kind of try to help them on that mission. But on the other hand, I think, so here's my kind of solidified, now that we've introduced what these things all mean, solidified kind of idea, which is we have the rules of the road, right? Like we have a little booklet, you're free to go to the DMV, pass your driving test. So like we should at least encode that somewhere. It's not that many rules. And the control system may be that plus a number of other important details. But it's impossible, I think, to encode all the nuances, even with kind of near infinite developer time, because you just end up kind of coding yourself in circles. So I think you want to make the best state-of-the-art kind of typical but good control system you can. And then what you do is, given that you're never going to get all the edge cases, you make it so that control system sort of outputs a confidence score of how sure it is of what it's about to do. And when that confidence score goes low, you want to fall back on a machine-learned control system that's been trained in lots of edge cases and may not be able to intuitively explain exactly what it's doing, but it knows that when there's a series of cones kind of coming into your lane, you just got to move over, right? Whereas there isn't a rule of the road, maybe there is, but like it doesn't really say how close those cones are, or wow, it didn't even warn me, So like there's a lot of those kinds of cases where I think the control system ought to have a fallback on something learned from data.
We'll take one and then the other. No.
Hi, Adam Kraft from Orbital Insight, using deep learning for satellite image analysis. Great talk. Sounds like you're doing some really cool stuff, especially with making training faster and embedded and small. Have you guys thought, because you have such an extensive set of tools, have you guys thought about going beyond autonomous driving and other?
I think after we IPO, we might get into some other things with autonomous driving.
Looking forward to it.
So part of how we got to where we are today was about a year ago, we put up a embarrassingly crude website advertising that you bring your data and neural net configuration to our cloud platform, which actually wasn't really set up, and we would train it for you faster than anybody else. And we weren't necessarily thinking that this would be our core business model. We wanted to kind of see what inbound interest came in on people who need a solution to this type of problem. And a few months later, when we did the kind of 80-20 analysis on like, where's the real kind of hindrance coming from, it was like, automotive plus like a couple of outliers. And so it was just so clear to us that if we were to dive deeper on one thing, it should be automotive. The other thing that, if we were to go forward with that kind of platform as a service business model, it's really hard, is I feel that the people who are developing new neural nets are actually too smart for us, in the sense that like they're going to want to create new layers, then we have to figure out how to like make it so they can execute them efficiently, and they're going to want to really hack things up in ways that like no sort of just config file of a neural net API could really handle. So we also, it's hard to figure out how to do that well and not be like a limitation on your customer.
So if there was like one other industry after automotive, what would it be?
Well, obviously satellite imagery.
Come on board. Come on board.
Yeah, I think more broadly like security and sort of here are feeds of data from cameras. Can we create value out of them? If we had another 24 hours in a day, I'd be looking more carefully at that. Is there a question over there?
Oh, okay. So
The best numbers, my name is Aurora Tripathi, I'm at Shadowline Labs. The best numbers I saw up there was something like 88.5, top 5.
I think that's right, yeah, and people have beat that since then, although they haven't reported speed.
Are you happy with that, or what can push it higher?
So we're in the autonomous driving things with things like pedestrian detection and lane segmentation and stuff. We're not satisfied until it's like 99 point several nines, right? So, given our limited team size, we could keep beating on this useful ImageNet benchmark, but doesn't really help us with our product, beyond what it's already done. Or we could keep adding more nines to our product. And so we've kind of, voted to go that direction.
So I just had a follow-on question. So, you're looking at frames individually. Have you looked at like any kind of sequence learning or temporal learning to improve that number any better?
Again, that number, maybe I confused things, isn't like the metric around our product and stuff. It's sort of just to kind of, kind of like at Google, they have to kind of sometimes go back to the academic benchmarks to be able to show what they've done because their own data is kind of, not something that they're ready to share, and we kind of feel the same way. So we've done that here. But to try to answer your question, yeah, I mean, in autonomous driving-oriented vision, which is not just labeling entire images, but labeling individual objects and segmenting and so forth, we certainly do sequence learning, and LSTMs and so forth, I think, are a great tool for, I mean, not gonna say we've entirely brought this to fruition yet, but I think tracking is one of the last areas of computer vision to become deep learningized. So, for anything that's kind of based on the semantics of what type of thing is in this place in the image, deep learning has already taken off, right? So classification and segmentation and detection and so forth. But for things where it's more about matching something between two images, which is useful for 3D reconstruction and tracking and optical flow and so forth, those are areas where deep learning has been useful but not a slam dunk yet. But we think the way probably forward to unify that is to learn tracking and detection in one go. And I think part of the reason people haven't done that well yet is because there aren't publicly available data sets for that. But we do label our data in terms of continuous, here's a video, let's follow that object, and so forth. So yeah, I think that's really promising, and we might kind of brag about how we do there at some point.
Remember to tell us who you are and where you're from?
Hi, I'm Craig. I'm an engineer here at Clary. Just wondering, do you guys have a simulator, and would you think something like GTA 5 would work for training something would transfer into the real world?
I think simulation's a really good tool, and we've started to make use of it, although I'm not going to say it's like in our core stuff right now. We have someone in our team who knows a lot about physics and has been sort of tinkering with game engines in general for both kind of doing lots of cases for testing the models as well as adding more training data. I'm not going to say, the jury's still out on like how beneficial that is. There are a lot of papers you read kind of every year at ECCV or CVPR, the computer vision conferences, where it's like they do the A/B comparison of like just natural images versus natural images plus a big pile of synthetic data, thrown all in one big hopper. And the big hopper of stuff often ends up with like half a percentage point more accuracy, which is good, but there are a lot of other ways we could have got there with less effort. So I haven't seen the cases either internally at DeepScale or outside where like adding simulated data to the training is like a big slam dunk, but would be silly not to try it. And GTA 5, I just don't know enough about it to like know whether it's optimal or not.
Hi, my name is Wenxin. I'm a student at Princeton University. I remember you originally trained SqueezeNet on AlexNet, right? And if I understand it correctly, you somehow removed the weights with small variance and retrained the weights with large variance and then squeezed the whole net. I wonder how well it's going to generalize to other networks. Like
so we actually didn't train, we trained SqueezeNet from scratch, not off of AlexNet.
Sorry?
We trained SqueezeNet from scratch, from just random weights, not off of AlexNet.
But it's just use less parameters and got the same result with
SqueezeNet is unrelated to AlexNet. Like, if we just wrote that in the title so people would say, oh, it's so much power than AlexNet with the same accuracy. But how that generalizes, yeah, I mean, we've seen opportunities across the set of things we're doing, for our job, where there are some parameters that are worth a lot accuracy-wise and some that aren't. And so one trade-off you get to make, given a fixed budget of computation, if you want to get to real time, you have this many flops per second you can do in your processor, and then you want to use a good chunk of them. So you might say, look, I've given myself a budget of for each image I get to do, I'll make up a number, like 5 gigaflops of computation. And so, okay, should I use those flops of computation for big activations and few weights, which doesn't require many, has few weights? Or should I use it on pretty small activations with lots of weights? And the answer, it turns out, depends on the application at hand, which is sort of good, right? I mean, for us, if there were one universal neural net model that you could discover, our job would actually be kind of harder to be defensible, right? But as long as we keep finding new models that are great, we're kind of happy. Or if we find that rule and kind of use it. But yeah, I mean, it's certainly true that for every application, there's some model that works great there, and you want to find that model rather than trying to just use something that already exists and make the best of it.
Okay, got it.
Yeah, hope that helps.
So Forrest, great talk. This is Venkat here. I just wanted to follow up on one of the earlier questions about accuracy. I guess 88.5% accuracy is something that was not up to the mark, but
right.
I guess from a perspective of...
Can I actually address that a little better? So there's image net competition every year.
My question is, in terms of what I've read in, popular literature is rather than have a single source of a sensor, the accuracy dramatically improves if you had 3 cameras that are all, coordinated, and all 3 cameras are feeding, and by triangulating on obstacle detection, you have really 99.99% whatever you wanted from the perspective of really nailing what one camera couldn't do. But if you had, with motion and multiple cameras of the same steering around it, and sending multiple cameras to your neural network, you get much better accuracy. Can you elaborate on other techniques beyond just having one set of data?
Yeah, of course. I mean, so there are a bunch of ways you could do that. So you could try initially stitching all those cameras together and using the best stitching methods you can find. Or you could go more of an approach of, let me just have the neural net have a few different heads, let's say, that each take it, you kind of say the left image goes in this head, the middle image goes in this head, et cetera. And a few layers in, you might kind of concatenate or merge them together somehow, and then the last layers have sort of a, one cable all the way through. I think, so we're currently assembling a vehicle that will drive around and collect data, and we've gotten a lot of that together at this point. And it does have multiple cameras, and we have a bunch of things that we're planning to do with them. And yeah, I mean, more sensors is usually better than fewer sensors, and you kind of want to figure out which of them, which of that set of things you put on there is actually giving you the most signal, and kind of double down on that. But as you can imagine, for these ImageNet things and stuff, where you kind of scrape a bunch, they scraped a bunch of images off Google Images, and unfortunately, there is no Google Images for LiDAR yet, or YouTube for LiDAR for that matter. So that's been limiting on for the people who aren't collecting their own data on a vehicle, how they get the right data.
Okay, we have time for 2 more questions. We'll take one more from each side of the room. So a gentleman here, and then one more from the other side of the aisle.
Hi, Ron Bodkin, founder of Think Big Analytics. Great talk. I'm curious, you talked about some of the things you did that really helped in terms of speeding up training. What were the things you tried that you were optimistic about that didn't really pan out?
Yeah, so in Kurt Koitzer's research group at Berkeley, they've continued to experiment with distributed training. And there were a bunch of experiments that were done around recently that I don't think have been published yet, but they're around can we combine the benefits of asynchronous training with not needing a central parameter server? And there's this approach called gossiping SGD that they invented that sort of tries to do that. And they took a very respectably scientific approach at kind of doing the A/B comparisons in the fairest way possible. And it turned out that they evaluated a bunch of existing stuff with asynchrony and then tried this thing. And this gossiping SGD thing worked pretty well, but it didn't really beat the synchronous training by that much. So I guess we've tried, or we / the grad students who remain back at Berkeley have tried a bunch of things to try to outgun synchronous, sort of straightforward training, and we haven't found like the next 10x speed up.
Rich Liao from Caltech. You have used 3 kind of GPU from 3 big company, right? So are they the same for you, or they are